Okay, so in this course, or in this unit rather, there are two kinds of graphs that we are going to be primarily focused on. Okay, position versus time graphs, that's what our lab last week was about, and velocity versus time graphs. And we'll do a lab on that as well. Okay, for right now, okay, we just want to kind of look at graphing in general. Okay, how do we read stuff off of graphs? How do we interpret a graph? But specifically, position versus time and velocity versus time graphs are what we're going to look at. Okay, so this week's quiz will be on the stuff we covered today and tomorrow and Wednesday. It's all graphing. Okay. All right. So what we need to understand today, what kind of information can be read from the two kinematics graphs we just talked about, position versus time, velocity versus time. Okay? Understand that graphs and equations, so all the formulas on your formula sheet, are derived from the same place. Okay? They come from the same place. They just show data or manipulate data differently. Okay? And so that's kind of those last 2 points there. Okay, so position versus time graphs, okay? Like the one we made on Thursday when we did our lab. A position versus time graph shows us where an object is at the points of time that were recorded, or during the time interval that was observed. Okay, so a position versus time graph shows the position of the object as a function of time. Where was it at 1 second? Where was it at 2 seconds? Okay, so it is showing a vector quantity. Okay, position is considered a vector quantity because it can be positive or negative, east or west, north or south. Okay, it is a vector quantity in that way. All right, let's look at the graph here on the left with the green line. Okay, between 0 and 1 second, what is that object doing? Sarah, you're shaking your head. It's not doing anything. How do you know that?
It's not moving.
Right, it's a horizontal line, right? On any kind of graph, a horizontal line means there's no change in whatever's on the y-axis. Okay, in this case, what's on the y-axis is position. So that means that between 0 and 1 second, the object hasn't moved. It has remained at a position of positive 20 meters. Okay, everyone follow the interpretation there. Okay, so between 1 and 3 seconds, what does that object do? Is it moving then? Okay. Forward or backward? Forward, right? Its position is becoming more positive. That would indicate it's moving forwards. Okay. Is it accelerating or moving at a constant velocity? This is the harder one. We all want to say accelerate because we see a diagonal line. We see an increase in something. But here's the thing. Acceleration is a change in velocity. This object isn't accelerating. Its velocity is constant, and here's how we can find out. Between 1 and 2 seconds, the object goes 20 meters. Between 2 and 3 seconds, the object also goes 20 meters. Is it going any faster? No, it's covering or changing its position by the same amount every second. That's what velocity is. Okay? Velocity is an object's rate of change of position. Okay? Weird thing here. We've only looked at this formula in this way. Okay? That velocity is displacement divided by time. But also on your formula sheet, okay, is this formula. That displacement is final position minus initial position. Okay, can I read position right off of this graph? I can. So could I calculate the displacement of this object between 1 and 3 seconds? I can. Its final position is here, 60 meters. Its initial position at time 1 second is 20 meters. 60 minus 20 is 40. Okay, 60 minus 20 is 40. Okay, so it went 40 meters. It displaced itself 40 meters in a forward direction during that time. Okay, so could I calculate its velocity now with this graph? I could just go final position minus initial position divided by time. 60 minus 20 over 2 seconds. Right? Because between 1 and 3 is 2 seconds. Everyone follow me there? Okay, so what's 40 over 2? 20. Is that exactly what we said when we drew the jagged line there? Yeah. Every second it went 20 meters. So when you see a diagonal line on any kind of graph, it means that y is changing at a constant rate. Okay? On a graph like this, that means a constant velocity. Okay? Because the position changes by the same amount. So we can say during that time, it moved at a velocity of 20 meters per second forward. Okay? So here's what we want you to do, or what we hope you will do. We want you to learn the analytic skill that we just did, which is look at the graph and determine what's going on. We don't want you to memorize this graph. Okay? Like in Science 10, you only have 2 graphs. You could probably memorize it and get away with it and get by, although I still see people mess up even with only 2 graphs. Okay? Why we want you to learn how to analyze it is because of the number of graphs you're going to have to deal with in high school. You can't possibly memorize them all. So it's better to learn how to analyze a graph like what we just did. What's going on here? Well, the position is changing, and it seems to be changing at a constant rate. What's a constant rate of change of position? Well, that means it's going the same amount every second. That means constant velocity. We want you to be able to analyze like that as opposed to memorize it. Does that sort of make sense? Because that analytical skill can be applied to any graph. Okay, and that's what we're going to focus on as we look at position, time, velocity versus time graphs, is using that analytical skill versus memorizing. Okay? Everybody with me so far? Okay. What is the object doing between 3 and 4.5 seconds? Not moving. Okay? It stays at a position of positive 60 meters, right? Between here and here, its position does not change. It does not move for that 1.5 seconds. Okay. What is it doing between 4.5 and 6 seconds? Okay, we want to say that. That's the most common answer I get because, again, we see a decline, right? And that means it feels like it means slowing down. Is it changing its velocity? It actually isn't, right? If it's an incline, if it's a diagonal line of any kind, then the rate is constant, okay? So this thing is actually moving backwards at a constant velocity. Okay, so there's 1.5 seconds of time here. So if I break this up into kind of 3/4 seconds, okay, that would be kind of here and here, okay? Those 2 lines, this line and this line, are the same length. Okay, that means every time interval, it goes the same, or changes its position by the same amount. That's a constant rate, okay? That's, in this case, a constant velocity, because velocity is your change in position over time. And if that's a constant rate, okay, that's what that's showing. All right, in this case, it's moving backwards. How do I know that? It goes from 60 to 20, right? It backtracks what it did before. Okay? So is its displacement during this time the same amount as here? Right? Here we calculated the displacement to be positive 40 meters. It went from 60 to 20. Can I calculate the displacement here? Yeah, but now, okay, it's still final position minus initial position, but now it's 20. 20 is the final position minus 60. 60 is the initial position for that section. Okay, what's 20 minus 60? Negative 40. That means the object went backwards. Okay, these are the kinds of interpretations I want you to be able to make on a graph. To be able to look at this graph and go, not moving, moving at a constant velocity forward, not moving, moving at a constant velocity backward. Okay, be able to look at a graph and interpret that. Okay? All right, where does the object go faster? Here or here? On the downward part, how do you know? Just a guess? But something led to that guess. You had an instinct. What about this line makes you feel like this line is faster than that? Exactly. It's steeper. Okay? That line is steeper. And if we mathematically look at what steeper means, it does the same amount vertically in less time. Right? This one here took 2 seconds to go 40 meters. This one only took 1.5 seconds to do the same thing. Therefore, it's going faster in that section. Okay? That also means then, and this is the part that could be important for you on your lab, that the slope represents the velocity of the object. The steeper the line on this kind of graph, the faster the object is going, because it changes its position more quickly. Okay? And again, that's not something you have to memorize. Okay? That's something that we can just analyze. Okay? That's what Thomas did. He looked at this line and went, that one's faster. Okay? Instinctively, he knew that steeper meant faster. Okay? Why does steeper mean faster? Because we did the same amount vertically in less time. Okay? This had the same amount vertically. Those two lines are equal. Okay? But that line is longer. Okay? Steeper hill. Okay? We changed our position at a faster rate. That's a faster velocity. Okay? Everybody all right with that? Okay. What's the total displacement on this graph? 0. How'd you know that? Okay, so you looked at it logically and you said it went up 40 and then it went down 40, so it didn't go anywhere? Yeah, absolutely true. Okay, could I also look at it this way? Okay, we've said several times displacement is your change in position. What's my final position? 20. What's my initial position? What's 20 minus 20? Okay, mathematically comes out to 0, right? Either way works. Okay, if you're a visual person, you look at that graph and automatically go, let's look back to where it started, but it didn't go anywhere. Okay, but you can also mathematically prove it. Okay. Everybody all right with that idea? Okay. Now, this is also a position versus time graph. What does that object do? That object is accelerating. Okay, does it look distinctly different than the other graph? Yeah, it's curved. Okay, now here's what a curve means. Okay, a curve means that what y is doing is not uniform. Okay, its change is not uniform. Okay, this line here on this graph, the change in y was uniform. Every second it went up 20. That's not what's happening here. In this graph, in the first second, okay, the object changes its position by only this much, that little red line. But in the next second, it changes its position by that much. And in the second after that, changed it by that much. And in the next second, even more. And in the next second, even more than that. Okay? The only way you can go farther in the same amount of time is if you are going faster. Okay? So acceleration would look like this. It's showing me that y is changing at an irregular rate. Okay? Or the rate at which y is changing in and of itself. It's not constant. Okay? Everybody okay with that idea? All right. So is that object speeding up or slowing down? Speeding up, right? It's going further every second than it did the second before. Okay? So what would this graph be showing me? That's slowing down. Okay? Because if I put on the time increments here, okay, in the first second, it goes that far. In the next second, it only goes this far. And in the second after that, it only goes that far. Okay? It's going not as far every second. Okay? That means it has to be slowing down. And eventually, this line would become flat. And if it's flat, the object's not moving at all. Okay? That would indicate it would definitely be slowing down. Again, that's the kind of interpretation we want you to get to. Because we'll look at that shape and go, what's happening on this graph? Okay? Oh, I see a flattening curve. Okay, well, a flattening curve means whatever's on y is not changing as much, or the rate at which it changes is going down. Okay? All right. Everybody okay with that so far? All right. Last week, 2 days last week, we talked about drawing a graph, being able to get the equation for the line, calculating the slope, that kind of stuff. So we're going to kind of quickly review that. Okay? So obviously, we're very concerned about using this formula. Okay? We want to use it whenever possible. It only applies if we have a straight line. Okay? So that's the kind of line you got on your graph on Thursday. It's just a straight inclined line. Okay? It doesn't work on a graph that has like flat spots and angled spots. It doesn't work there. Okay? It works on this kind of graph only. Now, on this graph, I'm just going to draw a better line in here, guys. Okay? This point right here, okay, if I went across to here, that value would be y, okay, from my equation. Okay? In fact, any point along that line could be y. Okay? What is this point? It's the y-intercept. What part of the equation is that? Thought I heard somebody whisper. This is b. Okay? That's the y-intercept. B represents the y-intercept. Okay? What is the value of y when x is 0? On this graph, this is the initial position of the object, where the object was at time 0. This would then represent the final position of the object. Everybody okay with that? Because position is on the y-axis. Okay. What would this point be from the equation? That's x. Okay? I mean, this is the x-axis, right? This is the value of x at y. Okay? So what does m represent then? The slope. Okay? So the slope of the line is m. Okay? Now, you might have been taught in math that you can calculate slope by going rise over run. Okay? And that would be y2 minus y1 over x2 minus x1. Okay? That's absolutely true. But that formula is horrendous if you're solving for anything other than slope. Okay? It's really difficult to use if you're trying to solve for anything other than slope. So that's why we use this formula. This formula can also calculate slope, okay? Because that's m. How would I manipulate this equation if I wanted to get m by itself? Subtract b, yeah. Okay, so I would have, so we'll start like this, y equals m times x plus b. So I would subtract b over to the other side. So y minus b now equals m times x. How do I get m by itself? Divide by x. Okay, so this is one way to calculate slope. This is the change in y. Is this also the change in y? Right? Y minus b would be this. Same as y2 minus y1. Works, okay? And in this case, I just have x on the bottom because x1 is, what's x at b? 0. I don't need to put in x1 is 0. I don't have to go x minus 0. I can just write x. Okay? This calculates slope just as well as this does. The benefit of this formula is I can use it to calculate other things a lot more easily, which is what we learned how to do last week, and is what questions 2 and 3 on the analysis of your lab are also asking you to do. Okay? So use that formula. Okay. Now, here's the next thing we want to talk about, and then we'll take a little break. On every graph, I mean every linear graph, there's a slope. But on every linear graph, the slope represents something different. Okay? We don't want to memorize what the slope on every graph we encounter is, because we can always figure it out. That's the skill we want to have. How do I figure out what the slope represents on this graph? Okay, so here's how we do that. Okay, we already kind of talked about this, but the slope of this line is actually the what of the object? The velocity. Okay, this is the velocity of the object. Okay, here's how we figure that out though. If I look at this formula, so if I have y minus b over x equals m, on this graph, I just have to look at what are these actual numbers. Okay, on the y-axis is position. Okay, y is my final position. B is my initial position. So y is final position. B is initial position. What's x? Time. What does that formula calculate? Pretty sure that's this. What does displacement over time calculate? Velocity. Okay? You can always figure out what the slope of the line represents by just putting in what's actually on the graph. Okay? That's all we did here. We looked at this and went, oh, it's a position versus time graph. So on this axis, our final position and initial position, that would be measured in meters. Okay? And then time is on the x-axis. Well, if I divide meters by seconds, I get meters per second. Those are the units for velocity. Okay? This represents velocity. Okay? And you can do that on any graph. Absolutely any graph. Okay? All right. I'm going to give you a 4-minute break within the room here. Okay? And then we're going to pick up. Okay, so let's have a look at this graph here just to kind of, practice these analysis kind of skills. Okay, so it is again a position versus time graph. I can see it's meters on the y, seconds on the x. Okay, what's going on in part A? Okay, moving forwards, yeah, going up, so moving forwards. Okay, constant velocity or accelerated? Constant velocity, because the rate at which it's changing is constant. Okay, there's no curve here indicating that the change in position is increasing. Okay, all right, what's going on in part B? Not moving, right. Okay, what's going on in part C? Okay, going backwards. Does it go past where it started? It does. Okay. What's going on in part D? Not moving. What about E? Okay, it's going up. Is it moving forwards again? Okay, is it still behind where it started? Yes. Okay, where is the object going faster? E or F? E. Because E is steeper. Okay, remember, this is change in position, right? Okay, they actually change their position by about the same amount, but E does it way faster. Okay, steeper means faster. Okay, everybody all right with that idea? Okay, I want you to calculate something for me. Let's assume that this whole trip goes to 18 seconds, just to simplify things. Okay, what's the total displacement of this object? Okay, that didn't take very long. Why is it 0? All right, it starts and ends at the same position, which just happens to be 0. Okay. Calculate for me now the total distance traveled. Because that's not 0. This is like that trip to Walmart thing we did. Okay? So, if you're going to get the total distance, you need to know how far it goes in total. Does that mean you need to figure out how far each section is? Okay, get to it. Figure out how far each section of this graph is. Okay, and then tell me the total distance traveled. Okay, I'll try and make it a little easier for you so you can see where all of these kind of start and end. So I need to figure out how far this thing goes in every section. Some of those sections are really easy because the answer is 0, right? For B and D, basically it's 0. All right. How did we figure out how far it went in part A? Part A is easy, right? It started at 0 and went to 6. So how far did it go? 6. Did you really just do this? You did. That's how you get each section of the graph. It's also how we got the total. Final position minus initial position always tells us how far it went and in what direction for that particular time interval. Okay, so here 6, here 0. All right, for this one we go from positive 6 to negative 10. How far is that? 16 meters. Negative 16 if we're talking vector quantities, okay, but we're not. I'm going to write it as negative 16 and then just ignore that later. Okay, D is 0, and then from E it goes from 10 to negative 4, so that's, or negative 10 to negative 4, so that's 6, okay, positive 6, and then it goes from negative 4 to 0, that's another positive 4. Okay, so 10 plus 16 is 26, plus 6 more, 32 meters is the total distance traveled for that object. Okay, here's a quick one. What's the average velocity of this object? Average velocity. How come I don't have the answer yet? I should have the answer already. It's 0. Why is it 0? Right, the displacement is 0 in this question. Okay, this is what happened on the quiz, right? We got the distance and the displacement, velocity and speed mixed up. Okay, I went and made you do a scalar thing and then I asked you a vector question. I'm going to do that all the time. You're going to have to be able to switch gears quickly. Okay, velocity is total displacement divided by total time. And we already figured out that displacement was 0 meters. Okay, doesn't matter what the time is, but we said it's 18. 0 over 18 is 0. Okay, now this one does require you to actually do a calculation. What's the average speed over the whole trip? So if I want to calculate average speed, total distance over total time. We already calculated the total distance is 32. We were told the total time is 18. 32 over 18, 1.78 meters per second. I'd say usually 2 decimal places. Okay, you'll learn about significant digits when you get to the 20 level sciences, and then there's a rule. Okay, everybody follow what we did there? That's exactly the kind of thing I'm going to ask you to do on a quiz. Here's a graph, do a little analysis of the graph, do a little calculating with the graph. Okay, if it's something linear like on your lab, use y equals mx plus b. Nothing we're not going to do lots and lots of times in class. Okay, a little bit of practice, and you get the hang of how to analyze graphs pretty quick. Okay. Now, something about position versus time graphs. We don't actually require you to do this anymore, okay? Simply because it requires basically some hand drawing on a graph. But once in a while, you'll hear the term instantaneous velocity. Okay? What that means is how fast was the object going at this point, rather than average velocity, which was how fast was the object going over this section of time. Okay? Instantaneous velocity means at this point in time. All right? So the way we would do that is, if we're looking at this graph here, what's going on in this first part? So I'm just going to put it in red here. From the beginning of the graph to there, what is that object doing? That object is accelerating. Okay? Because we can see that the position is changing at a non-uniform rate. Okay? It's going further than it did the second before every second, and that means it's going faster. Okay? If a question wanted me to answer, how fast is it going right here? How would I do that? I can't use v equals d over t because it's asking about an instant in time. Okay? What some people say is, well, I just go distance divided by time, and that would be it. Except that that's not for that point. That's actually an average between the beginning and the end. It's not how fast it was going at that point. It's how fast it was going over the time up to that point. It's not the same thing. Okay? So here's what we have to understand about curves. I'm going to teach you the only thing I understood in university calculus. It was the first day. I understood nothing after that. I passed the course by memorizing the examples in the textbook and writing them down on my final exam and getting part marks for method. I kid you not. Yeah. It worked because that was smarter than half of the class. And since it was graded on the curve, it didn't matter that I failed. Curves are awesome. You guys heard of the curve before? Okay. This thing called statistics, bell curve. Okay, and it basically means your grade is determined not by how well you do, but by how well you do compared to everybody else. I only had to do better than half the people and I would pass, even if I only got 38 on the exam. True story. As long as you're smarter than half the people, you pass. Sweet. Okay, I surfed the curve in that class, and then I got crushed by it in psychology, and I got a 95 and got a 4 out of 9. Sucks. Okay, back to this. So here's what I understood on the first day of university calculus. To a mathematician, a curve is an infinitely large number of infinitely small straight lines strung together. So when a mathematician sees this apparently smooth curve, they see it like you would see a low resolution picture on the internet. Okay? What can you see if the picture is in low resolution? You can see the pixels. Okay? You can see the individual boxes that a computer uses to make smooth edges. Okay? Most of the time, the pixels are small enough that we don't see them and we perceive that to just be smooth. Okay? Well, a mathematician sees a whole bunch of little straight lines, and they just get steeper as it goes along. So, to a mathematician, to calculate the instantaneous velocity, to calculate the instantaneous velocity simply means if I draw a line on here, and I make that line so that it is tangent to the curve, so it just touches the curve at that point. Okay, that's what tangent means, right? It just touches the curve at that point but doesn't cross it. Then they can cheat. That line I just drew is parallel to that infinitely small straight line that exists at point A. Can I calculate the slope of the line I just drew? Since it's a position versus time graph, would that slope be the velocity of the object at that instant in time? Okay, this is why we don't actually do this in class anymore. It requires you to actually draw a tangent line. Okay, and you can see that they drew one here, the dotted line, and mine is slightly different. And there would be a range of acceptable lines. So I would have to go and look at every single individual line and go, is that okay? It's close, but this one's okay, but that one's not, and they're only 0.1 off. Okay, so at some point, even though you kind of knew what to do, you lose a mark. So we just don't do that anymore. Okay, as long as you understand that. Okay, I'm not going to ask you to do it, as long as you understand the idea that a curve is made up of lots of little straight lines. Okay, now if we're looking at this graph, okay, we said the first part, the object is accelerating. What is it doing here? Decelerating, okay, because the line's getting smaller. Yeah, it's getting less, it's getting flatter, right? And we know once it gets to flat, it's stop. Okay, so how fast is the object going right there? Well, let's remember how we said the slope of the line is the velocity of the object? Here's that line drawn tangent to that part of the graph. What's the slope of that line? 0. So that object stops for an instant at the top of that line, or at the top of that curve. Then what does it do? But it already stopped. You can't decelerate anymore.
Oh, then it goes faster.
Right, it goes faster, but in a negative direction. Now it's going this way. Okay, these two parts of the graph here, are they the same? Like, are they mirror images of each other?
Yes.
Okay, that means they have the same acceleration. Right? Now, between here and here, now the object is that curve getting flatter? Okay, is it slowing down?
Yes.
Okay. What is this a graph of? It's a totally unfair question. Let's see. Something going up and down?
Yeah.
Exactly. Right? This is a graph of this. The first part of the curve is me accelerating the marker, making it go faster and faster. This part of the graph here is the part where it's in free fall. Okay, it goes up, it slows down because of gravity. Gravity slows it down, Thomas. Gravity slows it down, It comes to a stop for an instant and then falls right back to my hand. Okay, this up and down part, they're mirror images of each other. Okay, other than the fact that in one part it's up and the other part it's down, they're exactly the same. And then this last part is when I catch it and slow it to a stop. I would never ask you a question on a test like that. It's completely unfair. But I could ask you, what's going on in this part of the graph? What's going on in this part of the graph? The parts that's unfair would be, what is it? Okay? You got like a 1 in a million chance of guessing that's something thrown up in the air. Okay? But you could easily tell me what's going on in each part. Okay? It's slowing down, speeding up. All right. We're going to do velocity time graphs another time. I want to do some position versus time graphs here. Come on. Okay. I would like you guys to give this question a try. I believe it's in the workbook package if you have that. Okay, if you don't, you can just use the board here. Okay, so we've got a position versus time graph. Can't use y equals mx plus b here because there's different things going on. Okay, I want you to calculate. It's not meters per second. Okay, so the answers are there in bold. You can check and see if you did it right. Okay, but I want you to calculate the total displacement, the total distance, average velocity, and average speed. Okay, formulas you need are on the back of your formula sheet. Okay, but just in case. There are the ones that you would need. Okay, so on this one here, first thing we want to do is calculate the total displacement. Okay, this formula right here calculates displacement and it uses the things that are on this graph. Position, okay, and time. Well, it actually doesn't use time, but it uses position. All right, so if displacements are change in position, all we have to do is read our final position. Okay, 0.5 meters minus our initial position, positive 0.2 meters. Okay, and positive 0.5 minus positive 0.2 is positive 0.3 meters. Why is the positive important? Is displacement a vector quantity?
No.
Yes, it is. Yes, it is. That's why it has to have a positive on it. Okay, if you just write 0.3 meters, you're wrong. Okay, that is not the displacement. Positive 0.3 meters is the displacement. Can you go get a drink of water?
I'm out of water.
Go fill it up.
Thank you.
And then we'll scare you when you come back and get rid of your hands.
Okay.
Okay. Any questions on part A there, how we did that? Okay. Now, total distance. That I can't just do with one simple calculation like that. Now I've got to do it piece by piece because I need to know how far does it go in each section. Okay, how far does it go here in the first second? 0. Stays at a position of positive 0.2 meters. Then it goes from 0.2 to 1. How far is that? 0.8. Okay, then what does it do here? Stays still, so 0 there. Okay, and then it goes from 1 down to 0.5. How far is that? 0.5. Okay, so 0 plus 0.8 plus 0 plus 0.5 should be 1.3 meters. No vector on that. Distance is scalar. And it doesn't care whether you go forward or backward, just how far did you go. All right. Now, we've done all the heavy lifting now, believe it or not. Okay, to do parts C and D. All right, so for part C, we want to calculate the average velocity. Well, average velocity is total displacement, which I calculated in part A, divided by total time, which I can just read off the graph. It's 7 seconds. Okay, so to do average velocity, all I have to do is take 0.3 positive divided by 7 seconds, and I will get positive 0.04 meters per second. Is the positive important there? It is. Velocity is a vector quantity. Okay, I have to indicate that this thing ended up 0.3 meters forward of where it started and moved at 0.04 meters per second forwards on average. Okay, average speed. We've already done the heavy lifting for that. We calculated the total distance, so all we have to do is plug our numbers in to this formula. So that'll be 1.3 divided by 7 seconds, and we get 0.19 meters per second. No vector on that because speed is scalar. That's just how fast the object went on average. Okay. Everybody all right with that? Okay. They don't really get a lot harder than that for a quiz or a test. Okay? You could get a straight one like you have for your lab. Okay, but in terms of what kind of position versus time graph might I give you? Something like that. Okay, maybe I'd make it go into the negatives just to, throw something a little different in there, but right, it's not going to be a whole bunch of jagged lines or anything like that. Okay. Let's try this one. Right, so you got this again, position versus time graph. Right, I want you to answer A through D there. So part A wants us to calculate the total distance traveled. All right, so for this one then, that's scalar. Okay, direction doesn't matter. I have to do this one section by section. All right, so in this first section here, we go from 0 to 400 meters. How far is that? 400 meters, yeah, it wasn't a trick. Okay, then for this section here, how far does it go? 0. Doesn't go anywhere. Stays at 400 meters for the next 30 seconds or so. Okay? Because it's flat, right? There's no change in position there. And then over the next 2 sections, I could break it up section by section, but really I'm worried about the total. It goes from 400 back to 0. How far is that? 400 meters. Okay, how far does it go? 800 meters. It went 400 up and 400 back. Okay, it went 800 meters. Simple as that. Okay, I don't know why I have 600 meters there. Oh, sorry, between 0 and 90 seconds. That's why I have 600 meters there. Only to there. That's 200 meters. That's why it's 600. Not over the whole trip. Okay, everybody with me on that? Okay, you gotta stop me if I make a mistake. I'm sure most of you did that right. I didn't. All right, the displacement from 20 seconds to 80 seconds. All right. Displacement is final position minus initial position. Okay, the final position will be at 80 seconds. So I go to 80 seconds. Okay, so final position is 300. My initial position is at 20 seconds. That's here. Okay, 200. So when I do this calculation, positive 300 minus positive 200 is positive 100 meters. Okay? Pretty simple calculation. I just have to find my initial and final positions on the graph. Okay, questions on B? All right. Average speed over the whole trip. Okay, so over the whole trip, if I want to find average speed, I need the total distance and the total time. The total time is 100 seconds. I can read that right off the graph. What I don't have is the total distance. Okay, I know this is 400, this is 200, this is another 200. So 200 plus 200 plus 400 is 800 meters divided by 100 seconds is 8 meters per second. Okay, no vector on that because speed is scalar. Okay. All right, and then for D, average velocity over the whole trip. Okay, average velocity is total displacement divided by total time. Now, just looking at this graph, does this object come back to where it started? So what's the total displacement? 0. And if the total displacement is 0, so is the average velocity, because it would be 0 divided by 100. And anything with 0 in it is going to be 0. Okay. Questions there? All right, we haven't had any that go into the negatives yet. All right, that's next. All right, so position versus time graph here. Okay, same idea. This one just goes down into the negatives. Doesn't really change anything. You just have to make sure you include those. This one. All right, so displacement from 0 to 4 seconds. Okay, so at time 4 seconds, that's our final position, -4. Okay, our initial position is obviously 0. Okay, so our total displacement, final position minus initial position, is -4 meters. -4 minus 0. Okay, for part B, total distance traveled. Okay, so in this section here, we go from 0 to -4 meters. Then we don't go anywhere. And then we go from -4 to +6. That should be +10. So our total distance traveled is 14 meters because distance doesn't care whether it's positive or negative. All right, average speed over the whole trip. Well, average speed is total distance divided by time. So that's going to be 14 divided by 6. Okay, and that'll give us our 2.3 meters per second. And then average velocity over the whole trip. Okay, that one's probably the most work. Okay, it's total displacement divided by total time. That's final position minus initial position over time. So that'll be positive 6. Listening, please. Why are we packed up? I'm not done. Neither are you. Pull your books out. Positive 6 minus 0. Okay, and we're dividing that by, obviously, 6 seconds. 6 divided by 6 is positive 1 meter per second. Now, if I gave you that one on a quiz, you'd be surprised how many people will forget to put the positive on D and the negative on A. It's vectors that get people all the time on this. Okay, you have to remember when you're solving for a vector quantity, and put on the appropriate vector on your final answer. Okay, tomorrow we're going to work on velocity versus time graphs. Okay, and then Wednesday, just graphs of all kinds. Thursday, we've got grade 10 maths. Okay, so we won't have much class time. And then Friday will be your quiz on graphs. Okay, so I'll put the practice quizzes up here, and you can check those out, okay, this week.